Optimization and simulation of a navigation robot in mazes. Abstract path planning has been relatively well known in the fields of robotics, especially on autonomous navigation robot. It has the capability to venture from one place to another by using the optimal path acquired from path planning method. Not only that, path planning has also been implemented for maze solving. Throughout the years, many scientists had been formulating all sorts of path planning algorithm, whereby they are implemented on a navigation robot for experimental testing in real-life mazes. Therefore, this study will focus on 3 selected path planning algorithms, A*, breadth first search and left-hand rule, where a comparison test will be conducted to acquire the most appropriate one among the rest. The selected one will then be added with enhanced feature, where it will be simulated in a 2D graphical rendering surface. After this, the path planning algorithm will then be implemented in a physical constructed robot, where it will be tested again in a physical maze. The findings and results will be discussed accordingly. Keywords: path planning, A*, algorithm, breadth first search algorithm, left-hand rule algorithm, mazes, navigation robot. Introduction. In recent years, navigation robot has been widely used in performing tasks such as rescue operation, disaster relief, and space exploration. One of the noteworthy features that can be considered is their path planning capability. Path navigation is a process where the route or path that is planned must be correct to ensure that the navigation robot is able to move safely and freely without getting lost or colliding with other objects too. It has been relatively well known in the fields of robotics, where it plays an essential role in the navigation of autonomous robot 3. Although path planning has coexisted alongside autonomous robots, it is still unable to obtain a universal solution for. In recent years, various kind of path planning algorithm had been developed. Each algorithm has their own specific aspect, where some requires the information of the maze while others do not. Hence, 3 selected path planning algorithm techniques, namely A*, algorithm, breadth first search, BFS, algorithm, and left-hand rule, LHR, algorithm, are selected for comparison and examination, where the most appropriate one will be chosen and implemented with enhanced feature. Moreover, the path planning algorithm will also be tested in a physical navigation robot and maze. 2 path planning algorithms. A*, algorithm. A*, algorithm is known as the best path planning algorithm, where it can be applied on any topological configuration space 5. The algorithm is a combination of both exhaustive search and greedy search 6. Exhaustive search guarantees an optimal path but requires long computational time. Greedy search excludes the optimal path by obtaining the overall search with less computational time 7. Both exhaustive search and greedy search are represented as the movement cost and heuristic cost of the distance. Furthermore, A** relies of 2 lists, namely an open list and a closed list 8. The open list contains a list of nodes that can be traveled to, while the closed list contains all the nodes that had already been traveled. The algorithm will check all adjacent nodes from its current location and add them together into the open list. The current location will be added with the adjacent nodes that are included into the movement cost. At the same time, the heuristic cost will be computed for those adjacent nodes that have not yet been calculated. 9. The equation for movement cost can be seen, where n is the movement cost for both adjacent node and current node, and is the row and column coordinate for adjacent node, while n is the row and column coordinate for current node. The lower movement cost on adjacent node will be prioritized. 9. The equation for heuristic cost can be seen, where represents the calculated heuristic cost, and represents the row and column coordinate of the desired ending location, while n represents the row and column coordinate of the adjacent node. The summation of both movement cost and heuristic cost will be evaluated as the fitness cost. It will be listed in the open list, while the node with the lowest overall cost will become the new current node 10. The equation of the fitness cost can be seen, where represents the fitness cost, represents the movement cost and represents the heuristic cost. The whole process is repeated until the desired ending location is reached. B. Breadth First Search, BFS, algorithm. Breadth First Search algorithm is an algorithm that is used for traversing either a tree or graph data structure 11. The algorithm works efficiently by visiting and marking all the key cells in an accurate breadth-wise fashion in the graph. It expands the cell into different levels respectively while utilizing the first in, first out, FIFO, manner to visit the nodes 12. The ordering is based on the enumeration of cells in a graph where the possible output is applicable. Hence, using graph, G equals, V, E, and a source cell, the BFS will traverse the edges of G to find all the reachable cells from. At the same time, the algorithm will also compute the shortest distance to any reachable cell. Any path between 2 points in a BFS tree will correspond accordingly from the root to any other node S. In maze solving, BFS is used to find the goal cell from the given source cell. Starting from the source cell, the overall layer of unvisited cell will be visited and added into the visited set 13. As mentioned, BFS algorithm will label each cell from the start to all neighboring vertex while marking the start cell as 014. The algorithm will constantly update the cell that are immediate neighbors from the start cell. The search continues until the goal is found. See left-hand rule, LHR, algorithm. Left-hand rule algorithm is recognized as the most common wall follower algorithm 15. This algorithm operates by taking precedence to the left-hand side in the maze 16. Therefore, when the algorithm is placed into the maze, it will run accordingly by sticking to the left-hand side at all times. As the algorithm reaches an intersection, the left side will take priority first. If the left side is open, the algorithm will turn left then move forward. Otherwise, it will check to see whether it can move forward or not. If there is no forward option, the final resort is by turning right 17. 3. Methodology. Fig 1, Project Overview. The overview of the project is categorized into two parts, namely hardware and software. The software part will cover mainly on the comparison, selection, feature added and implementation of the path planning algorithm into the navigational robot. First and foremost, the three selected path planning algorithms will be tested and evaluated using three different maze size, namely 5x5, 10x10 and 15x15 in Python software platform. This is to verify the most suitable path planning algorithm in terms of time and number of paths taken. After that, the selected one will be added with new feature and tested on the Python software. Moreover, the path planning algorithm code will be implemented into the physical robot through Arduino software. On the other hand, the hardware side will cover mainly on the construction and development of the physical robot and maze. This includes the hardware purchase and gathering, the connection of various components and material. For results and discussions. A comparison test. The path planning algorithm was tested in the Python program, where the results can be seen in Figure 2, Figure 3, and Figure 4. The white block represents the wall of the maze while the block in black color represents the empty path in the maze. Moreover, the green color blocks represent the searched paths and the yellow blocks represent the optimal paths. Two criteria were used to evaluate the performance, namely average time and path taken. The time will cover the beginning where the algorithm starts to solve the maze until the optimal path is attained. Nonetheless, the path is taken for each step the algorithm takes during the process. The result on each path planning algorithm can be seen in Table I, 5x5, Table 2, 10x10, and Table 3, 15x15. Based on the comparison made on each path planning algorithm on different size of maze, the most appropriate one to be chosen was A** algorithm. LHR algorithm had used the longest time and highest path taken, whereas BFS algorithm had used moderate time and lowest path taken. On the other hand, A** algorithm was the only one that had used the shortest amount of time and path taken, thereby chosen as the appropriate one among the three. B feature added to the path planning algorithm. The A** algorithm was added with a new feature where 2D Pygamy capability was implemented. The implementation has provided user with more freedom and flexibility in designing the maze size instead of initializing it in the Python code. The flowchart can be viewed in Figure 5. A 2D program window is generated once the Python code runs. At this moment, the user can freely design the maze based on their own discretion. The user can position the starting point, ending point, and the wall of the maze. Besides that, the user can also remove the blocks if needed. The user's design must be able to ensure that the path planning algorithm is able to solve it, else the whole program will generate an error. Figure 6 shows the sample result of the added feature. See Physical Maze and Navigation Robot. D simulation. Fig 9, simulation result in Arduino IDE serial monitor. The feature added A** algorithm Python code was written into the Arduino code. The information regarding the 3x3 physical maze is coded into the program as well for simulation purposes. The generated maze in Arduino can be seen in Figure 9. The information within the maze is initialized respectively, where 0 will represent the path, 1 will represent the start position, while 2 represents the wall, and 3 represents the goal position. Once the goal is reached, letters will be displayed in the bottom side of the serial monitor with the direction of movement needed for the navigation robot. Figure 10 depicts the intended movement on the navigation robot to solve the maze. The respective movement for each direction can be elaborated in Table V. Conclusion. In a nutshell, the objectives stated in the report were achieved. 3 path planning algorithms had undergone comparison tests successfully using the Python simulation program in PyCharm. Next, a new feature was added and implemented into the path planning algorithm where a free space with designing capability can be done through the incorporation of Pygamy library. The feature was added and tested successfully on a 2D window program simulation. Furthermore, the path planning algorithm was implemented into the physical navigation robot. The code was written in Arduino language whereby the grid was used for representing the maze virtually. The experiment was done successfully whereby the navigation robot was able to finish the given maze. Acknowledgement. I would like to express my gratitude and sincere thanks to my research supervisors, Dr. Yew-Hao and Dr. Chuah Yea-Dat for their invaluable advices, guidances, and enormous patience throughout the development of the research.